Imagine asking a state-of-the-art multimodal AI to tie a knot in a rope.
Right, a classic physical task.
Exactly. So it generates this stunning high-resolution video of a robotic arm picking up the rope. But instead of actually looping the fabric over itself, the arm and the rope just like phase right through a solid metal table, like a ghost.
Clipping right through the geometry.
Right. The text-based AI is producing beautiful pixels, but it is completely failing at fundamental physics. So welcome to AI Paper Slop. Today we're looking at a wild July 2026 paper called UniVR, Thinking in Visual Space for Unified Visual Reasoning. It's out of Beijing, Jiaotong University, and ByteDance.
It's a really fascinating one.
It really is. The core insight here is that our current frontier models rely way too heavily on text to understand the physical world, and that text dependency is exactly why they fail at complex, long-horizon visual tasks.
Because text just isn't designed for that.
Exactly. So to solve this, the researchers built UniVR. It's a 34 billion parameter unified model based on EMU 3.5. And it reasons directly in the visual space with zero language supervision.
Which is huge.
Massive. They pull this off using a novel reinforcement learning paradigm called VR-GRPO. It combines a global evaluation with a highly targeted step focal reward, basically forcing the model to obey the laws of physics at every single step of a generation.
Yeah, and the results speak for themselves.
They really do. They saw up to a 25% improvement on a brand new visual reasoning benchmark called VRX. And get this 34 billion parameter model actually beats text-heavy behemoths like Gemini 3 Pro on long-horizon manipulation.
Yeah. Let's unpack how they actually pulled this off.
Yeah, well, to really appreciate the mechanics of UniVR, we first have to look at the architecture it's replacing, right?
The old text bottleneck.
Exactly. If you examine the current standard for multimodal generation, whether that's pipelines involving Gemini 3, GPT-5, or Qwen 3, the fundamental mechanism is essentially a translation game.
The model ingests visual inputs, translates that visual info into a highly detailed textual reasoning chain, and then feeds that text into a downstream generative model, like NanoBanana 2 or GPT Image 1.5, just to render the final pixels.
It's essentially a lossy compression format for the real world.
That's a great way to put it, yeah.
Think about trying to teach someone how to ride a bike. Instead of letting them actually get on the seat, feel the balance, and intuitively understand the physical momentum, you just text them the physics equations for gyroscopic motion.
Right, which doesn't help them balance at all.
No, text is far too abstract. When you compress the physical world into discrete words, you drop all the intricate dynamics, the microspatial relationships, basically all the underlying physical laws that dictate how objects continuously interact in 3D space.
And the downstream consequence of that lossy compression is that even when these text reasoning models are paired with incredibly advanced high-fidelity video renderers,
they still mess up.
They mess up constantly. The final output is just riddled with physical inconsistencies. We see severe logical gaps emerge the second a prompt requires fine-grained, multi-step actions.
Like the knot tying.
Like the knot tying. Or if you prompt a system to fold a shirt or assemble a wooden block puzzle. The text chain might correctly say, loop the red rope over the blue box, but text cannot convey the topological reality of those actual objects.
So the resulting video just shows clipping, floating objects, and impossible geometry.
Exactly.
Well, let me play devil's advocate for a second, especially for the engineers listening who have been testing these frontier models all year.
Sure.
Because models like Gemini 3 Pro and Qwen 3 VL, they are explicitly marketed as possessing elite multimodal reasoning. I mean, their chain of thought capabilities are staggeringly complex.
They are very impressive, yes.
So if a model can generate a highly detailed step-by-step text chain that outlines every single micro-movement a robotic arm needs to make, why isn't that textual precision enough to guide the video generator accurately?
Because the generative model rendering the actual video is still fundamentally blind to the continuous physics between those text keyframes.
Ah, I see.
It's conditioned strictly on those discrete text tokens. So a text token for the word knot doesn't inherently contain the structural tension or the collision mesh of a real knot.
Right, it's just a label.
Exactly. The visual generator receives the text and has to hallucinate the physics required to get from point A to point B. The linguistic reasoning of Gemini 3 Pro might be structurally flawless, but the translation back into the visual domain breaks down because the system never actually thought in continuous visual space.
It thought in words and then tried to paint a moving picture of those words.
Exactly.
So if translating to text is the exact bottleneck causing these physical hallucinations, The logical solution is to just stop translating altogether.
You have to bypass it completely, yeah.
You force the model to think natively in pixels. And that is the exact premise of the ByteDance team's framework with UniVR. Instead of outputting a textual reasoning chain, UniVR predicts the next frame distribution natively.
Which is much harder to do.
Right, but it models state transitions directly in visual trajectories.
And they didn't have to build this visual architecture from absolute scratch, which is clever. They leveraged EMU 3.5 as their foundational baseline.
EMU 3.5.
Yeah, EMU 3.5 is a 34 billion parameter unified generative model, and it uses a VQVAE style autoencoder.
Why is that specific architecture important?
It's crucial because it tokenizes both images and text into a single, unified, discrete vocabulary.
Oh, wow. So they share the same token space.
Exactly. By turning continuous pixel data into discrete tokens, the model can process the visual world using the same autoregressive math we use for language, but without relying on the language itself. EMU 3.5 already knows how to process the visual world as a sequence of tokens.
But having a strong baseline like EMU 3.5 is great, but they couldn't just jump straight into reinforcement learning, right?
No, definitely not.
The paper outlines a rigorous stage 1 cold initialization phase, which is essentially just supervised fine-tuning, or SFT. They started in a massive raw pool of 1.5 million video candidates. Then they used Piscine Detect and SIGLITE 2 to rigorously filter out bad frames.
They had to be super aggressive with the filtering.
Yeah. We were talking about removing close-ups, blurry shots, and most importantly, scene cuts. Then they leveraged Qwen 3.5 397B to synthesize highly specific question and answer pairs for the surviving videos.
Yeah, distilling it all down.
Distilling everything down to a highly curated data set of 310,000 visual reasoning trajectories. And every single sample was standardized into a strict format, a query image, an instruction, and the visual reasoning trajectory.
And that structural standardization is the entire point of the cold initialization. Because EMU 3.5's original pre-training was largely focused on entertainment, artistic editing, general visual fidelity.
Stuff that just looks good.
Yeah, exactly. It knows what a video of a person cooking looks like passively, but it doesn't inherently understand the causal, step-by-step logic required to execute a specific, minute-long physical task based on a prompt.
So it's learn the format of problem solving.
Right. The cold start phase isn't teaching the model what a rope or a box looks like. It's teaching the model the structural format of how to solve a problem visually. It establishes a strong mathematical prior.
Like when you get an instruction, generate a contiguous sequence of visual states to achieve it.
Exactly. And you mentioned the filtering tools earlier, like Piscine Detect. Those were vital. Because if there is a camera cut in the training data, the temporal continuity is completely broken.
Oh, and then the model learns it can just skip the hard parts.
Yes.
Yeah.
It learns that things can just magically teleport to achieve a goal.
Which completely ruins the physics engine you're trying to build.
Right.
You're shifting the model's behavior from generate an aesthetically pleasing video to solve this spatial puzzle.
Right.
But if we look at the trajectory of model training, dense SFT always hits a wall. The ByteDance researchers point out that SFT plateaus rapidly here.
It always does with heterogeneous data.
Yeah, I mean, if you are trying to teach a model to solve a top-down 2D maze puzzle and simultaneously trying to teach it long-term human physical planning, like folding laundry, the underlying math is just too different.
The scales are totally misaligned.
Exactly. The tasks have completely different temporal scales, vastly different domain knowledge, and totally different visual representations. Dense SFT supervision simply cannot reconcile all that into a single optimal policy.
Which necessitates the shift to reinforcement learning. You have to let the model explore the latent space and optimize its own pathways.
Which brings us to VR-GRPO.
Yes, the core innovation of the paper, Visual Reasoning Group Relative Policy Optimization. When they set up the RL pipeline, they immediately encountered a catastrophic failure with standard reward models.
Standard RL just didn't work.
Not at all. In standard RL for video generation, researchers typically use a vision language model in this specific case, Qwen 3 VL30B, to act as the evaluator, right?
Right.
So the generative model creates a video sequence, passes it to the VLM, and the VLM outputs a global reward, denoted as R sub G.
Okay, the global reward.
And this score is based on whether the final task was completed and the overall visual clarity of the video.
But the global reward acts like a shockingly lazy grader.
It really does.
Because the VLM is evaluating the video using text-derived world knowledge, it essentially just fast forwards to the final terminal frame of the video, checks if the objective looks complete, confirms the resolution is high, and just assigns a passing grade.
It's completely blind to intermediate physical violations.
Which creates a textbook reward hacking scenario, right?
Oh, absolutely. If the prompt is to tie a knot and the VLM sees a tied knot in the final frame with crisp rendering, it outputs a high global score. It entirely misses the fact that in frame 45, the model couldn't figure out the complex collision physics, so it just phased the robotic arm through a solid table to get the rope into position.
It's the exact equivalent of a math teacher who only checks the final answer at the bottom of a calculus exam.
Yes, perfect analogy.
The student faked all the intermediate steps, invented their own fictional math in the middle of the page because they didn't know the formula. But because they copied the final number from the answer key, they get an A.
And if your reward model cannot see the cheated steps, your generative model will mathematically optimize to cheat every single time.
Because hallucinating a shortcut is computationally way easier than calculating real physics.
Exactly. So if the global reward VLM is blind to the middle of the generation, you would need some sort of automated way to scan the intermediate frames, right? To flag the specific ones that break reality.
Without relying on human labelers, which would be impossible at scale.
Right. And that automated detection is the exact function of their step focal reasoning reward, or R-subs.
Step-focal.
They needed a mathematical way to proactively hunt down the cheat steps, and they do this by looking for uncertainty.
Uncertainty. How does that work?
So during the GRPO rollout phase, the model generates a set of trajectories, basically multiple different attempts at solving the same prompt. For every single frame across all of those rollouts, they use a CLIP image encoder to extract the feature embeddings.
Okay, getting the embeddings.
And once they have those embeddings, they calculate the inter-trajectory variance across all the rollouts at every single time step.
Okay, let's ground this logic for a second for the listeners. Think about it like gravity, right? If you drop a ball, there is only one physical path it can take.
Right.
So if you have 8 rollouts of the model trying to execute a simple physical action, the first few frames are going to look virtually identical across all 8 videos.
Because it's obvious what should happen.
Exactly. The variance is incredibly low. But right at the moment the task requires complex physics, the model doesn't fully grasp like the exact moment the robotic arm has to cross the ropes to form the knot. Its internal probability distribution flattens out.
It basically panics.
It panics and guesses wildly. One rollout phases through the box, one drops the rope, one just glitches into static. That massive spike in variance is the mathematical fingerprint of a model that does not understand the physics of the current step.
Exactly. High variance equals maximum uncertainty, which highlights the exact time step where the model's reasoning paths diverge.
That is so smart.
It is. Once the algorithm finds the peak of that variance curve, it pulls a short reasoning segment window specifically centered around that confusing time step. Then it forces the VLM to evaluate just that isolated segment.
But wait, how do they stop the VLM from just giving arbitrary absolute scores based on its own biases?
That's where the pairwise evaluation protocol comes in.
Pairwise, okay.
They show the VLM 2 different rollouts of that specific high variance step and prompt it to choose. Which one of these obeys physical laws better, option A or option B?
Oh, by forcing a relative comparison, you strip away the VLM's absolute scoring bias. Okay, so we now have a global reward, R sub G, and a step focal reward, R subs. And the researchers integrate them using a specific penalty formula.
Let's hear it.
The final reasoning reward equals the global reward minus a lambda coefficient multiplied by the absolute difference between the global reward and the step focal reward.
Visually, that's R reason equals RG minus lambda times the absolute value of RG minus RS.
Right, and they set the lambda coefficient to 2.0. But looking at this formula mathematically, we are penalizing the absolute difference between the global reward and the step reward.
Yes.
So if a model generates a brilliant final frame, but terrible intermediate physics, the difference is huge and the penalty destroys its score. But doesn't this introduce a completely new loophole?
How so?
Doesn't that just incentivize the model to lower its overall global quality to match a terrible step score? Like if it purposely generates a globally awful video, the difference between the global score and the step score drops to 0. The penalty disappears entirely, and it has successfully hacked the reward function again.
That is a great point. And in an absolute scoring system, that loophole would absolutely destroy the training run.
Right.
But the system prevents that collapse because of the pairwise evaluation framework we just talked about.
Yeah.
These scores are not static, isolated numbers. They are relative win rates against other generated trajectories competing in the exact same batch.
Oh, so if it downgrades, it loses.
Exactly. If a model intentionally downgrades its global quality to match a bad step score in an attempt to minimize the penalty, it will simply lose the pairwise comparison against a competing trajectory that actually attempted to succeed at the global test.
That's brilliant.
The GRPO algorithm naturally pushes the baseline up by forcing the rollouts to compete. The only mathematical way to win the batch to maximize the global win rate while simultaneously minimizing the penalty difference is to generate a trajectory that achieves the global goal while maintaining strict physical consistency at the hardest intermediate step.
And setting the penalty coefficient to 2.0 ensures that succeeding globally but failing locally is punished so severely that taking a reasoning shortcut is just no longer a viable strategy.
It fundamentally forces procedural integrity. The model can't hallucinate the final state. It has to earn it through contiguous physical reasoning.
Wow. Now, building this visually native RL pipeline is a massive engineering feat, obviously,
Right.
but it presents a serious evaluation project.
Yeah, big time.
Standard benchmarks for multimodal models are either heavily biased toward text comprehension, or they only evaluate really short, isolated 2-second video clips. None of the existing frameworks could actually test if UniVR learned long-horizon physics.
So to prove the pipeline work, they had to engineer a completely new benchmark, which they named VRX.
VRX.
It consists of 1.8K high-quality, long-horizon reasoning trajectories spanning 6 highly diverse task categories. They test visual guidance, robot manipulation, puzzle games, visual editing, visual search, and spatial perception.
And just to give a sense to the listeners of what these tasks actually look like natively in visual space, a visual search task isn't just identifying an object in a static image.
Right, it's temporal.
It requires the model to generate a sequence showing an agent navigating a cluttered environment to locate a specific hidden target. Or, like a spatial perception task, might require the model to generate a video predicting how a stack of irregularly shaped objects will collapse if you remove the bottom piece.
Which is pure physics.
Pure physics. And evaluating these complex trajectories requires incredibly robust metrics. They use a standard VLM score, scaled from 0 to 100, using Quen 3.5397b to judge overall task completion. But as we established, VLMs hallucinate and miss physical impossibilities.
They do.
So to completely bypass that linguistic text bias during evaluation, they introduced a secondary, far more rigorous metric, the Jane-Pio similarity score.
And this specific metric is a master class in representation learning. Instead of asking a language model if the physics look accurate, they evaluate the generated video using a VJPA encoder.
VJPA. That stands for Joint Embedding Predictive Architecture.
Right, exactly. And unlike models trained to reconstruct exact pixels or classify objects, VJPA is trained by masking out massive chunks of a video in a latent space and then forcing the model to predict the missing physical dynamics.
So it's essentially trained to predict what happens next abstractly.
Yes, meaning it inherently understands spatiotemporal coherence and real-world physical rules without relying on a single word of text.
They are essentially using VJPA as an automated text-free physics engine to grade the model.
That's exactly what they're doing.
They take the generated video from UniVR and compress the sequence into a 1280 dimensional latent space using the VJP encoder. Then they do the exact same compression for the ground truth real-world video of that task.
Right, and once both videos are mapped as probability distributions in that latent space, they compute the maximum mean discrepancy, or MMD.
So instead of comparing raw pixels, which can be noisy or stylistically different, they are looking at the strict mathematical distance between those two latent probability distributions.
Exactly. A lower JPA score means the mathematical representation of your generated video is incredibly close to the mathematical representation of actual real-world physics. It bypasses language entirely and just grades the raw physics.
So when you look at the results in the VRX benchmark using these metrics, the impact to the VR-GRPO pipeline is undeniable. At only 34 billion parameters, UniVR vastly outperforms its own EMU 3.5 baseline.
The jump is huge.
Yeah, on long-term planning tasks, its success rate jumped from roughly 35% to 60%. On general reasoning, it went from about 43% to over 64%.
And, the performance leap over the baseline is great, but the comparison against the frontier text-heavy models is where the numbers get truly wild.
Oh, yeah.
UniVR outperformed massive pipelines like Gemini 2.5 Pro paired with Nano Banana 1. It approached the overall performance of Gemini 3 Pro paired with Nano Banana 2 across the board, and it specifically beat Gemini 3 Pro on long-horizon robot manipulation tasks.
Wait, you have a 34 billion parameter model beating a multi-trillion parameter pipeline on long-term physical reasoning.
Simply because it doesn't have to translate its thoughts into text.
That is insane. And furthermore, the stability of the generation is unprecedented. Usually, if you force an autoregressive video model to generate past 10 seconds, the accumulated errors cause it to devolve into this hallucinatory mess of shifting pixels.
It just melts.
It melts. But UniVR proved exceptionally stable on continuous generations lasting well over 30 seconds, entirely because the step focal reward keeps its reasoning strictly anchored to reality at every high variance juncture.
And all of that physical capability leads us to what is arguably the most profound finding in the entire paper, the multimodal spillover effect.
This part blew my mind.
Right. The ByteDance researchers took UniVR, a model trained exclusively on visual reasoning trajectories, utilizing a visual space RL pipeline with zero text-based reinforcement learning, and they evaluated it on standard, text-heavy multimodal benchmarks like MMMU, MME, and Mathista.
So without being trained on text reasoning, its text reasoning improves significantly.
It did.
Think about how wild that is for a second. Imagine you spend all summer practicing a physical sport in the real world. You are out on the court, hitting tennis balls, feeling the tension of the racket, watching the arc of the ball, internalizing the physical friction and momentum. You aren't reading any books.
Zero theory.
Zero theory. Then you go back to school in the fall. You sit down to take a highly theoretical written physics exam about trajectories, aerodynamics, and kinetic energy. And you discover you magically score 20% higher.
That is exactly what happened here. By forcing the model to understand visual physics natively, the researchers intrinsically bolstered the model's linguistic reasoning capabilities.
It proves that visual world knowledge is foundational to all reasoning.
Absolutely. If a model deeply understands how objects interact in space and time visually, it builds a much stronger, grounded conceptual framework. When it's later asked to reason about those exact same concepts using text, it has a robust physical prior to draw upon.
Text is just the abstract label applied to the physical world. Vision is the underlying reality.
Exactly. If you master the reality, manipulating the labels becomes trivial.
Which brings us to what this all means for the AI researchers and engineers tuning in. This paper represents a massive fundamental shift in architectural philosophy. We are successfully proving that we can move away from text as the absolute bottleneck for world modeling.
It's a huge step.
The textual chain of thought paradigm is incredibly powerful, and it got us this far, but it clearly has a hard ceiling when it comes to understanding the physical world. UniVR proves that native visual thought isn't just a theoretical possibility, it is highly efficient and scalable.
It provides a very clear blueprint for the next generation of architectures, really. You don't need dense, highly annotated image-text pairs for everything anymore. You can use variance-based reinforcement learning to teach a model the continuous laws of physics directly from pixels, completely bypassing the linguistic lossy compression.
Which leaves us with this final provocative thought for you to chew on. The ByteDance and Beijing Jiaotong University team proved definitively that VR-GRPO and Visual Space RL can effectively transfer native physical understanding back into general multimodal intelligence. And they did it at just 34 billion parameters.
A fraction of the size.
It beat models 10 times its size on complex physical planning. So what exactly happens when we scale this exact visual RL paradigm to the multi-trillion parameter frontier models currently training in these massive data centers?
That's the real question.
Are we looking at a rapidly approaching future where text becomes a secondary, almost archaic modality for AI world models, completely surpassed by native continuous visual thought?
Well, the underlying math strongly suggests we are heading exactly there.